The wire starts with length L1 and a tension T1 acting in the negative direction here, so I labelled this as minus T1. It's in equilibrium, so there's also a force T1 in the positive direction pulling on it. Then it is stretched to a length L2, and the tension increases to the size T2, and of course the force balancing this out also increases to a size T2. The energy stored is equal to the work done against the tension in the string, so that means it's minus the integral of the force, which is the tension in the string, dotted with the displacement it's moved through. Because the tension in the string and the displacement are acting in opposite directions, we get an extra minus sign here. And the tension at length L is TL, and the distance moved is dl, a change in length. This means that the energy stored is equal to the integral of TL with respect to dl. We can work this out using a graph of the tension against the length of the string. If we mark on how the tension changes with length, we can have a straight line starting at zero tension when the wire is at its natural length L0. At L1 it has a tension at T1, and at L2 it has a tension T2. There in the graph is equal to the integral of TL dl, so it's the energy stored. This orange area is the energy stored at length L1, and the purple area is the extra energy stored when it's stretched at length L2. You can use this to work out the energy stored when this wire is stretched from L1 to L2.